My name is Ariana, and this is my video lab report for Physics 2212, Dr. Barron's Lab 4 Circuits. The purpose of this experiment was to demonstrate the conservation of energy within circuits, understand concepts of the loop and node rule, and examine the behavior of resistors and capacitors through an online model. The results of this experiment are that the current and voltage values given by the model match the predicted values, and in an RC circuit, the magnitude of the current is time-dependent. Here are some important background equations. Ohm's law relates voltage, current, and resistance. The loop rule states that the sum of all the electric potential differences around the loop is zero. The node rule states that the sum of all the currents flowing into the node equals the sum of all the currents flowing out. The models for this lab are an online ideal model where the system is the circuit and the surroundings are everything else. We assume that the resistance of the wires and the ammeter are negligible because the PHYS model assumes an ideal circuit. The first part of the experiment involves a circuit with two 1.5-volt batteries, two resistors, and two ammeters. Using the node rule, the current is predicted to be 0.02 amps, and the simulation matches the prediction. Place an ammeter with a voltmeter. The voltmeter reads 3 volts, while the other ammeter reads 0 amps, because there is no current flowing since it's an open circuit. Closing the circuit, the potential difference was measured across each segment, and the sum results in 0 volts, which is expected based on the loop rule. The current remains at 0.02 amps. Finishing the graph with potential versus position, the max voltage is seen at 3 volts, and then traveling across both resistors, the voltage went back to 0 volts, with the drop being steeper along the 100 ohm resistor than the 47 ohm resistor. To answer the question, when you attach the voltmeter, why does the ammeter reading change? The voltmeter has a very high resistance and therefore very little current flows through it, so the ammeter doesn't change. After constructing the parallel ammeter circuit, the current splits between the two paths, and since the ammeter has zero resistance, this means that all of the current avoids the 100 ohm resistor and creates a higher current, 0.06 amps, because of Ohm's law, I equals V over R. Also, using the values found in the model, different resistances were calculated and the calculated answers were close to the ideal model values. The second part of the experiment involves a circuit with a 10 ohm bulb, a 20 ohm bulb, 9 volt battery, and 200 millifarad capacitor. After connecting batteries to the bulb and capacitor in series, I noticed as time progresses, the bulb grows bright and then dims until going out, which was the charging stage. The same thing happened when the battery was disconnected, which was the discharging stage. Using a stopwatch, I measured the time it took to charge and discharge. For a 10 ohm bulb, it took 9.3 seconds to charge and 10.1 seconds to discharge. For a 20 ohm bulb, it took 19.4 seconds to charge and 20.4 seconds to discharge. For the third part of the experiment, I plotted potential difference as a function of time over the course of 30 seconds and linearized the graph. This graph represents a circuit with a 30 ohm bulb, 9 volt battery, and 200 millifarad capacitor. Using the line of best fit from the graph, I calculated the RC value to be 6.8 seconds, while the expected RC value was 6 seconds. This results in a percent error of around 13%. Comparing the online ideal model with the calculations either perfectly matched or very close to the PHYS model results. One source of error was likely human error since the online model was ideal. Specifically, there is human error in stopping the stopwatch when finding times for charging and discharging. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? Well, an ammeter in real life has a small amount of resistance, so the circuit current readings would be slightly lower, as we assumed during the lab that the resistance to the wires and ammeter is negligible. But if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? To answer this, if there was no resistor in the circuit, the ideal model would show the capacitor charging immediately. But in real life, all wires have resistance, and that would slow down the charging process. Thank you.